So far, we've talked about linear scaling. Distances scale linearly with respect to the coefficient of scaling. Here, this distance is x, and then we scaled it by coefficient k, and then the new distance is k times x. So the relationship between x and k times x is linear scaling by the coefficient k. And I say linear because k here is raised to the first power. If it was k squared times x, then it would be quadratic scaling, because we scale by a factor of the square of the coefficient of scaling. And here we only scale by a factor of the first power of the coefficient of scaling, which is k. So this here is linear scaling. So what would quadratic scaling look like? Is there some quantity? Of course, it couldn't have been distance because distance scales linearly, but what other quantity could scale quadratically instead of linearly? It turns out there is one, and that quantity is area. The area of the triangle actually scales quadratically with respect to k. Let me show you what I mean. We know that under homotity with this center, this segment maps to this segment and now becomes k times larger. And also this triangle, the small triangle, maps to the large, the green triangle. And we're interested in how the area of the small triangle changed when it turned into the large triangle. And the answer lies in the ratio between the areas of the two triangles. If we take the ratio of the areas of the large triangle and the small triangle, it would be exactly k squared. To illustrate this, consider putting the initial triangle in a square like this, such that the bottom side of the triangle matches the bottom side of the square. Now I'm going to scale all of this by a factor of 2, such that this point here stays fixed. Let's say that I scaled by a factor of 2. So if this had length x, now this has length x, and this is x, and this is x. Now this triangle here, the large triangle, has twice the sides of this small triangle. And of course the large square has twice the sides of the smaller square. Now let's see what happened to the area. We can actually construct 4 congruent squares like this. So suppose that this square is the same as this square, is the same as this square, is the same as this square. Of course, they all have side lengths of x. Then the area of the square increased by a factor of 4. So when we applied homotity with this center and coefficient 2, the area of the square increased by a factor of 4. And 4 is 2 squared. And that's why it increased by a factor of 4, because it increased quadratically. The area gives quadratic scaling with respect to the coefficient. And so because the coefficient was 2, the area increased by a factor of 2 squared, which is 4. And now let's see what happened to the area of the triangle. Let's call the area of the small triangle here S1, and the area of the large triangle, let's call it S2. Let's call the area of one of the small squares, let's call it A, and then this area is A, this area is A, and this area is A. Now consider the ratio S1, so the ratio between this area and the area of the square that contains it. We can visualize this ratio here. You can see S1 divided by A. This is the red area right here, divided by A, the area of the square. And now let's try to visualize the ratio S2 divided by 4A here. So S2 is the area of this triangle, and 4A is the area of the large square. And now we can see that it's actually the same picture, that I can draw an arrow like this, because I can turn one picture into the other by just putting a 4 right there, and then the large square will be represented by this 4A square, and the large triangle will be again the same shaded in red triangle. And so the ratio between S1 and A, and S2 and 4A, they're represented by the same picture, so they're the same ratio. You see, when I put the small triangle into the small square and the large triangle into the large square, the triangles took the same amount of area with respect to their respective squares, because they're similar triangles, and the pictures here look exactly the same. They're just scaled by some factor. And therefore, these two ratios are actually equal. And so, S2 must equal 4 times S1, because that's the only way in which this equality can hold. And so we saw that if we take a triangle and we scale it by a factor of 2, its area scales by a factor of 4, or 2 squared. And we can do the same thing for a number that's not 2. For example, for 3, if we take by a factor of 3, we can take instead this picture, and then the small triangle would look like this, and the large triangle maybe will look like this. But in any case, the area here scales by a factor of 9, because the area of the large square is now 9 times the area of the small square. And the two triangles take up the same amount of area relative to their corresponding squares. And so we get the same thing as here, but instead of 4, we get 9, which is 3 squared. And we can generalize this for any number k. And this argument works not only for triangles or squares, it also works for donkeys. Suppose I have two congruent donkeys, so now they have, of course, the same area. But now I'm going to scale one of the donkeys by a factor of 2, like this. Now, what's the relationship between the area of the small donkey and the area of the large donkey? Well, the area of the large donkey is 4 times larger. Why? Well, because the area of the square is 4 times larger, and the ratio that the area of the donkey, for example, like this area, takes with respect to the small square here, is the same as the ratio of the area of the large donkey that it takes with respect to the area of this square that contains it. And because these two ratios are the same, but the areas of the squares differ by a factor of 4, then the areas of the donkeys should also differ by a factor of 4. So that's what it means to say quadratic scaling. Quadratic scaling is when the area of the large donkey, SLD, equals k squared, the area of the small donkey, SD. And in this case, k equals 2, but in general, k can equal any positive number. Can you think of a situation where we have cubic scaling? Oh, just follow the progression. Angles have a power 0 scaling because they don't change. Suppose I take an angle alpha, then it equals k to some power times the transformed version of alpha, the scaled version of alpha, which is also alpha because the angle didn't change. So I should put a 0 as the power of k, and now k to the 0 is 1, and the equation is true. So angles scale not linearly as with power 1, they scale by power 0. Lengths, if we have a length L, and we scale it by a factor of k, we're going to get its transformed version, L prime. Areas, if we take an area S, and we scale the picture by a factor of k, then the new area S prime is going to be k squared times S. And now, volumes, which is the next step, they scale cubically. So if we have a volume, V, we multiply by k to the third to get the scaled version of the volume, which is V prime. You can imagine if I have a cube, and then I scale it by a factor of 2, so here's the cube. I'm going to get a cube with side lengths 2, 2, and 2. So it's going to look something like this maybe. And I can find 8 copies of this little cube inside of the large cube, because 8 is 2 to the third. The optional problem for today is a bit unusual, and the question is simple. Can giant people exist? Is it possible that giant people exist? What do I mean by giant people? I mean, if this here is a normal person, a giant person would have exactly the same proportions, so it would be a scaled version of the normal person, but it would be 10 times larger, so that would be so large I can't even fit it on the screen. So for example, if the radius of the head of this person is 25 centimeters, here the radius of this head would be 250 centimeters, or 2.5 meters, because it's a giant, and every length in the giant person is 10 times every length on the normal person. So can these people exist in the real world? That's the question. Here is the solution. Suppose that such people existed. Then let the mass of a normal person be m. Then what's the mass of the giant? So the giant has mass. So mass, it's related to the amount of volume the person has, and volume scales cubically. And so the mass would be 1000 times the mass of the normal human. Now let's consider another quantity, and that's the area of the foot. The area that's in touch with the ground. For example, if this is the ground and this is the foot of a person, then I mean the area right here that touches the ground. This area, let's call it A for the normal person. This area for the giant will be 100 times A, because areas scale quadratically, and the scaling coefficient is 10, so 10 squared is 100 and 10 cubed is 1000. And now we can calculate the pressure on this area by this mass. And in the case of the normal person, the pressure is force divided by area. And the force is m times g, g is the acceleration on Earth, divided by a. And in the case of the giant, it would be 1,000 times m times g divided by 100 times a, which is 10 times mg over a, which is exactly the same quantity here. So the giants would feel 10 times the pressure on the area below their foot. So imagine what would happen if 10 people with the same weight as you just jumped onto your shoulder. In this way, you would have 10 times the pressure on the bottom of your feet. And how much pressure that would be. The feet would probably not be able to support this kind of pressure, which means that if such giants existed, they would have to live under a lot of pain.